Hello again, everyone. Um, Hope you're well. I think most people have joined and are starting to join, so I might start with just like the introduction and recap. But yeah, I see that Indira, you've uploaded the recordings and the resources after the session, so that's also good resources for everyone to have. So yeah, let me uh, someone share my screen. There we go. Okay, so. We reached the middle of the program. We're in lecture 3. Um, I'll sort of like just gloss over this. This is resource just for the structure of the lecture. A little bit of a recap of what we've been talking about. So in lecture 1, we started with like the introduction over the energy challenge, building blocks of energy systems, and examples of existing tools. Yesterday, we explored how these sort of real world systems can be started to be conceptualized and approximated into models through certain mathematical formulations and the need for the optimization type of problem as the size of these problems grows. Today, we are going to be looking at why we use Stevens. So we've been talking a little bit about Stevens, sort of like mentioning it in the background, and introduce some of the like main and most important formulations behind it. So first off, we're going to go into key concepts glossary. This is mainly for you to have a resource, but as a reminder for throughout this lecture, we'll be talking about some of these things. So at least in Stevens, an asset will be any physical component of the system. So that will be either a technology like renewable energy, solar, PV or wind, an HVDC cable between two locations, or it can be the demand center for a certain location, whether that's electricity or heat. Then we have location. So that's just the geographic node of where a technology or demand center, different asset will be located. We have energy vectors, which, as we described yesterday, is the form that energy will take or the carrier that it will have, whether that be electricity, heat, or a certain fuel. Capacity factor, this will be the fraction of the maximum possible output that an asset, a technology can achieve at a given hour. So this will be the capacity factor profile for renewable energy, or it can be defining for a specific like thermal power plant, what share of the maximum sort of like nameplate or installed capacity is able to be actually generated. Then we have the brand or a type of asset. In Stevens, we have these two set to be able to set like different scenario values, versions. So we have a specific version of an asset type, and this can be like if we have 3 versions of solar PV, we might see that one of them is a higher cost than the other one, or a certain power plant might emit more CO2 equivalent than another one. So different brands help us define this in the same sort of network and scenario. And we have a case study, and that will be one fixed network structure. We'll go into this a little bit later as well. So you can have like the distinction between case study and scenario. And the scenario will sort of like be the set of parameters that you define a case study with. So a single case study can have many scenarios if the same sort of like network structure is applicable to all the scenarios that we have. And finally, the trade-offs, that's the tension between different competing options. Like we were talking about examples yesterday, like cheaper fuels, but maybe higher capital cost of a certain technology and that sort of thing. So these are themes that are going to be coming up soon. And now we're going to go into Stevens and why we've chosen this model. So it's a quick little recap from Monday. There are many, many energy system models available, whether they be open source or proprietary software. Here's a table of, again, like the examples and their main focus, even though we keep in mind that a lot of them will do several different things. So why have we chosen Stevens? Why are we modeling in Stevens? Stevens is designed to combine multiple modeling needs within one single framework. So it uses a generalized technology model to be able to harness different modeling needs and answer a couple of questions at once. So it can capture both long-term decision making, so that is what and how much it will build, while also optimizing short-term operation with certain like assumptions and caveats, obviously to like reduce the problem for more tractability and to be able to run it faster. And it represents the system using these physical relationships that we were talking about yesterday. So the energy balance, that fundamental rule, and the flows in between the different nodes of the system. So it's a simplified but generalized technology models to achieve these. The whole optimization framework is built in a way that it can perform rapid scenario analysis, but also with optimization. Sometimes optimization, depending on how detailed it is, it can take very long to run, while those like simulation tools that we spoke about yesterday can perform like things very rapidly. So Stevens tries to capture both things to a level of reliability where results might be useful to start analyzing. So as we spoke about like case study and scenarios, once one specific network, which is where and which types of technologies are going to be located and how they might be connected in between each other. The model can be very quickly rerun by changing parameters such as technology costs, efficiencies, resource availability, or deployment limits, for example, or any other parameter that you want to test certain what-if questions for the scenarios. You'd be able to create like one big scenario, one big case study, and then run many options for that. This is achieved sort of like just a background detail. We're not going to go into much detail about like how this works, but Stevens uses a structured convex optimization framework, and that's an open source library as well, so a Python library called CVXPy. And this does that thing of like parameterizing the problem so that once you build it, which is sort of like the more time consuming part of it, once you've built everything, then if you change values, you can very quickly run it. This obviously includes like certain abstractions, like using this generalized technology model, which has its limitations as with any other model. I want to specify a couple of caveats for the current version of Stevens that we have. The long-term decision planning is currently abstracted to assume that builds like happen overnight, sort of like building a system from zero, which is this greenfield assumption. And then it just determines to operate over a long period of time, depending on asset lifetime. So like it decides if I need to install a PV power plant, a PV farm now, that will operate through its entire lifetime. But if our project is longer, that means it might be replaced. So Stevens does take into account these future costs into a net present value assumption. But in the current version, at least, we don't have a specific when. This is something that is being developed currently to have that understanding of like both what and where is cost optimal to build, but also have that like when tracking. So this is, yeah, just like to track assumptions and things happening behind Stevens. So why is all of this important for data collection? And again, like we're coming back to that comment of the model is as useful as the underlying data that we provide. So this is going to reflect on the results very directly. So every single decision is based on those input parameters. And that's why we can build scenarios that will give us different results depending on the certain costs or efficiencies that we use for different technologies or assets. Okay, so we've been talking about this background and framework and sort of like this conceptual thing of like what Stevens is and why we've chosen to use this model that links these different capabilities. But what is it actually? So very straightforwardly, the Stevens is an acronym for space-time energy vector flow networks. Space, like we spoken yesterday, the model can optimize across multiple locations simultaneously, and each can have its own parameters, technology, cost values, demands, resources, etc. Time, the model can see the system at every hour up to a whole year at the moment, and with this captures sort of like all of the hourly, daily, and seasonal variation. There are time reduction techniques available so that if you have a very big problem with like a lot of technologies in a lot of locations, if it becomes too big, reducing the amount of time steps that you sample will help for faster solving. With this, there can be some changes in results when you reduce the time steps because it's solving a slightly different problem every time. But the effects of that can be tested, and there can be a level of a point in which the time reduction doesn't change the results as much as it would if you like choose only for say like 1 day sample versus half a year of a sample. Maybe still faster than running the whole year, but the results might not change as much. So it's worth that time saving in running the model by reducing the resolution. Then you have energy vector. So this is because the model tracks multiple vectors using the generalized asset model and the conversion between them. So converting, for example, electricity to heat or to hydrogen or other fuels and back into electricity, that can be modeled. And flow networks, this is because the locations and the asset, everything forms that interconnected network that we were talking about. And we're going to see more examples a little bit moving forward. So what do we optimize? We're optimizing across like 3 main dimensions. So this will be the asset or the technology sizing, how much of each new technology that we have given the option for the model will be installed for the cost optimal result. Gigawatt peaks of solar or the size of a battery, etc. At the same time, the asset operation, so hourly or at each time step, what is the best with the sizes, what is the best sort of operation in this cost optimal solution? And asset location. If we have better solar resources in one of the locations than in the other, then it's probably going to be better to have that solar in that higher resource location. All of these are interdependent with each other. So if we have too much solar, the battery or the storage that we need might need to grow so that like excess can be stored enough and it can be moved in time. Or if we have only solar and no wind, we only have like these renewable peaks. So then we're going to need a flexible power plant or a battery to discharge during the times that it's not, that the sun is not really shining in the location that we have. So how does Steven set up this framework? What are the 3 languages that communicate within each other? We have these system design, asset modeling, and optimization languages. So I'm going to go from right to left, just in a little bit of detail. The optimization is that core mathematical formulation of like what's going to be the objective function, how are we going to build the constraints, what are going to be the parameters, everything that goes into that, and how we build the problem. Then we have the asset modeling language. So like a level on top of that, we come in and we decide, okay, we want to create a new asset. We want to now model a cooling asset, for example. So we need to actually use the generalized coordinates and that generalized technology model to build this new asset within the framework and be able to model it and see results. And finally, we have the system design language. And that's where we come in to like decide like what kind of data, what parameters are we using, what the network will be. So what are the potential locations that are interesting to look at, what technologies are possible to be installed in each, and what types, so the brands of the technologies. We're going to be focusing on this side because that's where like the input parameters come and where the data collection effort sort of like makes its impact. And we're going to leave the asset modeling language and optimization language as something like fixed. This is more for like model developers to look at. So the system designer language, so we're like zooming into that. Firstly, we have the asset itself. So we define what the type of asset we have, if it's a cheaper PV or a more expensive one, the locations that it has, and the start time and end time define the sample size of the model that's going to use for like optimizing the whole thing. So if we have a start time and end time that cover 760 hours, that will be the whole year, but we can shorten this before. And then we can have several brands that have different parameters. Then we have the energy system. So that will be our network structure. So here we have like that minimal example, right? So we have two locations. In location one, we have this asset, and the locations are interconnected by this other asset. So that's where you start building where you want your solar, where you want your power plants, where you want everything else. And each location will have its latitude and longitude and like a brand or type. So that's going to link. This is how we're going to communicate of if this asset that you've created is going to be in this location, then you can link those, and we'll see the format of how this actually looks a little bit later. So yes, everything that's highlighted in purple is defined by what will be modeled in GMPA. So to relate to that platform that we saw in lecture 1. And this will be what you'd be like helping collect. So how much more we're going to model and what different scenarios or countries we can add to the platform. So the brand parameters, these include these examples. So naturally, as I've been mentioning, like the capital cost of the total asset. It will also involve the operational cost, can involve efficiencies, losses, the total lifespan, which will help the model understand like when the asset will need to be replaced and how much that would cost in the future, an emissions factor, or any other relevant descriptor of a specific technology that you want to build. Okay, so the mathematical structure. So we're going to go a little bit back into what we were looking yesterday of the optimization and how things are defined in the context of STEVFNs. So as we're minimizing the total system cost, the objective of the STEVFNs problem will be to minimize the sum of the cost of each asset. So for the cost for asset alpha and the cost for asset beta, like all of the assets that we have in a system, their cost will be added in this function. And we're going to minimize that. So each asset will have its own cost function. Depending on how the assets are designed, they're going to have different operational capabilities and functions. For example, in a generalized way, so we could have that the cost of this alpha asset will be a function of its total size and the operation. Specifically, this could look like we have the capital expenditure of that asset alpha and the operational expenditure. These are two parameters that we input as model users. And you have the total size of the asset and the sum of the flows for the asset over time. So that's the operation. These two are the variables. This is what the model is going to be changing. So one, like it depends on one another. For example, if we are defining a power plant such that we want to like make it fully flexible, the problem we're going to create is going to vary all of these flows over time. And the size is going to be, let's say, the maximum of those. So like the peak, that's the maximum that it can provide. So that's how you would estimate the cost for that specific asset. And you have functions like these for each asset, which may change depending on what the design is. Okay, now we're going to be diving into constraints. So we spoke yesterday about how constraints are these limits that the problem will have, so that we can put these parts of like reality into how it's operating and not just let it run with like every single possibility that it could have. STEVFNs specifically handles this in the explicit constraints of the model, in not like energy balances or flow balances at the node level. So this diagram here represents, we have certain nodes. Specifically, we'll have this central electricity node that's like representing the grid. And we're going to be looking just at like one time step for now. So this is electricity grid at time step t. We have a system that has PV, that has wind, and that has a conventional power plant, so a CCGT, and it has a demand, right? So at time t, all of these have a value. All of the generation is coming into the grid, and the demand will be coming out of the grid. The problem definition makes sure that the sum of all of the inflows, so the sum of all of the generation minus the sum of all of the outflows, in this case we only have one outflow, has to be more than equal to 0. This ensures that at any point in time, so at each of these nodes like time t plus 1, time t plus 2, etc., this balance is going to hold. So we have at least enough energy generated that equals demand, or it may exceed it. This design decision is to allow for energy curtailment to happen. So the model will be able to solve if you have more generation than demand, but it will not be able to solve if at any point you have constraints on like how much the size of your power plant is going to be, and those like technical limits of PV and wind, and suddenly you have a peak in demand. If this is higher than the sum of these three, then you're going to have an infeasibility. So this just makes sure that we are meeting demand at every point in time for electricity. An example of what results may look like showing this, for example, we have this plot. This is showing for the 4 seasons over a year, an average day resulting from the model. We have this hourly power plant generation, hourly wind, and the solar. As you can see, solar and sometimes wind end up being curtailed because you have that excess. Throughout the year, the system must have built this because there were peaks in demand that required a higher capacity, and it might have been cheaper to install a higher capacity and curtail the energy than to try and meet it with like power plants. And you can see that at this time, then you don't need any power plant generation because you have enough renewables to meet at the middle of the day when you have those peaks of solar. Okay, so that was for a single time step and in just like the electricity node. But if we're trying to look at the picture, you could end up having a network like this. So we have location A on the left and location B on the right. We may have the same generation sources, let's say, and one demand center in each location. All of this is at time t as well. So this would happen at all of the times too. You'd have like nodes and edges built for all of the time, so the balance holds. In this case, for example, I've included as well, okay, you might be able to import and export electricity between the grid LTA and the grid in location B at LTB. So you have this interconnection between them and it can flow both ways. Similarly, you could try and import and export ammonia. So you have an ammonia asset that goes into the ammonia node. And from this location, you could have electricity to ammonia. So you're creating ammonia using electricity. Then you may ship it. And once it reaches this location, then it can convert it back. You could have, for this to be a bidirectional, you would have that electricity to ammonia also converting back. But the idea is that these node types, so we had a grid node type here that enforced that balance, but now we have an ammonia node type. And this also needs to enforce that the available ammonia coming in or out is always sort of like subject to that balance. Key takeaways, quick summary. So the model will choose what to build and how to operate it with that objective to minimize total system costs. The total cost will depend on how much is installed, which is that variable that we're allowing the model to change, and where it is and how it operates it. The system is interconnected through those nodes and edges, and at every node, which can be in different in time, type, or location, the problem constraints are enforced. So you define the system through the network design with data inputs and with assumptions, and the model will find that combination that will have that least cost. Now that we've seen how this can be defined, we're going to look at case studies and scenarios. So first of all, the case study will define that structure. So like that diagram that we saw of where things may be located and what technologies are. This table shows sort of like examples of what things will change for each. And the scenario will define what specific costs or parameters define that. So like how efficient or what the demand is in each of the locations. And the model for each case, you will run a case study at a time. And for each case study, it can run the scenarios with the new assumptions and produce results in a fraction of the time that it took to build it initially. So you can create many case studies that have different structures. So if you have 3 locations instead of 2, you'd need a new case study. But the scenarios within the 3-country case study will have to have that same network structure. Okay. So we have that sort of conceptual understanding of how these concepts in STEVFNs are built. But how do we actually like translate that onto model inputs and that's language? So I'm going to do a little bit of a live demonstration of the repository, and this is linked, and we will send the resources afterwards. So go in here. There we go. Yeah, there we go. Okay. So I've created a fork of the original repository. When you go into this link, this is the page that you're going to see. And this is available for you to come and play around with it. And that's going to be like part of what the assignment today is going to be. So the first bit that we see here is all of the files and how the model is structured. And I've created a file so that you can run through steps of how you need to set it up, create your branches and start editing and running the model. So if you go through this, you'll be able to see how this looks and what you can do to edit it. For example, if we're looking at that system designer language of we're going to look at the case studies, we would go into this data folder and to the case study folder, and then we've gone into test collab. So this is broken down like it's shown here. In this case study test collab, we have the network structure and we have one scenario folder. So this is just going to run one scenario, one version. If you have more scenario folders, this will be able to run for this network structure that many scenario folders. So now I'm going to look into the structure of this a little bit to walk you through it in person. I have that guidance prepared as well, so you can look at it and read it afterwards. But basically, the version of the sort of simplified diagram that I showed connected with like arrows would look like this file. I'll make this a little bit bigger. So we have an asset number, and this will just be sort of counting how many assets you have. Asset class, this will define what type of assets you're going to have. So for example, here we have electricity demand, electricity to high temperature heating. So that's like an electric kiln, for example, in real life. This would be the high temperature heating demand, how much energy is needed for heat, battery, and so on and so forth. And then you have some in a different location. So we have location 1 and location 2 columns. The important caveat here for user input is that if something is going to be just located in one place, both of these need to be the same location. You'll see when you have L transport, so electricity transport, that's an HVDC cable. It will go from location 0 to location 1. And this is designed to already be bidirectional, so there's no need to put 1 to 0. Just explaining just this, putting the 0 to 1 is enough for that bidirectional trade. And the same thing happens when you're transporting ammonia. So that's between these two locations. Then we have the start time and end time columns. These define the number of time steps that you're sampling from the model. So in this case, we're going to go from 0 to 192 hours only. That will run the model very, very quick and will give us like some initial results, or at least let us test that everything set up is okay. But you can increase this value, and you can also phase this a little bit forward, but this basically will start sampling at the start. This choice of sample size, what in the background, what Stevens does is it will grab 24-hour chunks of, let's say, like if you have the full demand hourly profile, it will grab those daily values spread out throughout the year in an attempt to capture the seasonal variations. So there's like different sampling techniques that we can do, but this is the version that we're choosing for Stevens. And we have period. So that's like the how often you are going to be sort of like generating or moving things around with that asset. For most of things that involve electricity or hour-to-hour handling, this is going to be 1. The exception in this case would be ammonia shipping. The assumption under this is that you're not going to every single hour be sending a ship of ammonia out of your model. The assumption is going to take 4 days, 96 hours is 4 days. And finally, the transport time. Again, for anything that like involves electricity or things that are in a single location, we're assuming that it's instantaneous, that we're going to be transferring things instant to instant, but the ship will take longer to get from one location to another. In this specific case, that's going to be, that's like 4 days and a half. Everything here is in hours. So that's how you define those times, locations, and what technologies are. So what the diagram looks like in things that the model can read. And then we go into the scenario definition. So there's 3 key things that we need to define in the scenario. System parameters, these will involve the discount rate that you want to use, which will help determine what the net present value of things are. The length of the project, which is in hours as well, so time step that you're using. In this case, this value corresponds to a 30-year project lifetime, and what time steps you're using. So you want to do those increases in 1 hour granularity. We also have location parameters. So the data that's included here currently is for these 30 locations. So we have coordinates for certain points within countries at this stage, but this could be different kinds of locations. If you choose to do a different system as a user, you can input different ones. The main thing to note is that the selection of the coordinates for this will be used to calculate an estimate of a distance between 2 locations. That will help cost the electricity lines between them, for example. That's the main thing that this is used for, and for some conventional naming for the model to find renewable energy profiles. But that is not like too important for now to get you started with the model. And then we have the location names. That's for, at this stage, this is for our guidance to understand like, okay, I'm using this location. Then to put this into the network, I need to see what this ID number will be, right? So for Singapore, we have 0. For Indonesia, we have 1. If you remember when we were looking at the case study, the network structure, location 1, location 2 are 0. So that is telling us that all of these assets are going to be located in Singapore, while all of these are going to be located in Indonesia, and there's going to be option of trading between them. And finally, the last key and required file for the scenario folders is the asset parameters. This is going to look a lot like the network structure. So we're going to have these first 4 columns, up to location 2 are going to be the same. And then we're going to have a column for asset type. This is where we're going to be defining those brands of if you have more expensive PV, or if you have different kinds of assets, or if you need to read a different PV profile from one location than from a different location, this is where you will define that. And to show you where these are coming from, this will come from the source folder here. We have an assets folder. That's where all of the technologies and all of the system components that are currently modeled in Stevens are found. So for example, Let's go into demand. Each of these will have this parameter CSV file, and this is where you will find those relationships. So again, we see that we have that same kind of idea. We have a type column or an ID column that will tell us the value that needs to be put into the network structure to link these files. So for Singapore, we've made it convention that it's the same number. This is the demand file that it's going to access for the demand. So going back here, this has a profiles folder, and we have one that is called Singapore 2050 gigawatts. That will have the entire demand profile. So that's how these things link with each other and where you would be able to change things. So if we go back to the network structure, we have that demand center at this location 0, and it's asset type 0. You'll see here that for all of the Singapore assets, we have that convention of the asset type being the same number. That just saves us the time of having to go back into that asset folder parameters and seeing what the type is. And all of the Indonesia ones have the same one. There is only, for these transport models, we only have one brand or type of parameter because there's no really these emerging technologies that are not that widespread. And we have just like a literature reported value. So that will just be brand 0. We will only have that value going here. So for example, in ammonia transport, you can see that here, there's only that one. That's how you can check like the data availability that is already embedded within the model, and things that you might like change or add if you're building something yourself. So, okay, so that's like sort of the walkthrough of how the repository looks. Notes on what I've mentioned are also written here. So you will find, for example, like what the structure of the files is and some instructions to look at. So obviously, because there's a lot of steps and a lot of links. So yeah, don't worry if, like the resource will be here and the recording of the session as well, in case you need to go back to it. And some instructions on like how you can start setting that up for yourself. Thinking about this, I want to just quickly show you a couple of steps as well, to have that set up on your laptops, as this is going to be part of the assignment. Just to like show you real quick, this is the part that is going to be shared with you later of like the setup requirements for the model, all of these steps sort of like very clearly defined. But let me show you a little bit of a workflow of how this looks like here. There. Okay. So I have opened up a terminal window here. You can open that like in Windows or in Mac. I don't know. I'm sure there's like a varied range of experience with people like using this or not using this in the session. So I'm just going to do like this quick walkthrough. So first of all, once that I've come in here and I'm in my user, I'm going to go into my desktop by running a change directory command. And I'm going to download or install the software there. So if I go here, I'll see this link and I'll copy that. And I can run the command git clone that link. That will take a couple of minutes, like just a minute or two. And it will create a folder in my, sort of like a local folder in my laptop that's called STEVFNs GMPA. I think with the call, this might take a little bit longer. So I'm going to cancel that and I'll just go into the version that I already have installed. Okay, so I have gone into this folder, right? Show you how this looks. So this is the same name as the repository, and it will have all of the files that you've seen online. And this will allow you to like edit them directly in your own computer. You will need to have installed a couple of requirements, which is Git and UV before you're able to run everything within your laptop. But one thing is, if you do have some experience with this and might have things installed already, a quick sort of check is to see if, okay, if I've installed Git, if I run which Git, it will tell me that there's something in there. Same thing with UV. I have installed it. If you haven't, then you can follow the install instructions, which are going to be linked in all of the guidance and everything there. This allows us to set up an environment to install the dependencies of the software. So that has been resolved. That should take a couple of seconds, not too long. The first time that you do this, it will display some other messages in green, and then just finish doing its environment setup. And now you should be able to run the model. So with the test case study that we have set up there already, you should be able to run a very quick test to see that everything is fine. So here you'll see in the README, you have this note, okay, quick run of the predefined collab test study. You can quickly copy it to your clipboard here and go back to your terminal. We're in this repository root, which is indicated by this Stevens-GMPA. So we can paste that there and run it. So starting to run it with Solr, we had some issues here with the structure. Might have changed something. But I'll confirm that everything is working with the branch, but it should then display this result. The exact number, depending on the optimization, it might be in the few decimals like slightly different, but don't worry too much about that. And I'll make sure that this is operational by when you need to test it. And you can then follow these instructions for setting up your own case study. There is, you can see the results of the total cost and total emissions of your system directly in the command line tools. But the problem also comes with some plotting functionalities where you will be able to see some like installed capacities and installed costs of the whole system. So that will look, for example, like this here. And I'll go back into this. So okay, before I just go a little bit through these slides so you know where things are there questions for this setup at this stage? Check. No, I don't see anything in the chats. Okay. So I'll continue with like what the asset will, what the assignment will include today. So you have similar guidance here on how to install and do the first quick run of the model. How to create your first case study with the data that's available. So the location parameters that I showed you from here, this will have the guidelines of data that's available for what types of locations. So for a quick run, you will want to choose something from here, except for the United Arab Emirates, that we don't yet have some renewable resources. So you might not be able to run that fully, but everything else has the data already incorporated within the system. And the assets, I put a list in the README here as well for the assets that have full data. Let's go back here. So that's his main thing. And when you're going through these instructions, it'll be, fairly clear. So we have these for now. Those are the main ones that have availability for everything. If you were to choose another one, you might have to go into that like source asset folder and so into that parameter CSV to see what's available. or if you need to like add data to it. So yeah, so that's the part of like what you can do for your own custom case study, and you can choose which technologies and locations to use from there. So the assignment itself will be to try and set this up for yourself if you can, using that workflow like sort of like shown here and with the resources that you have. Run the test collab case study. So that is to ensure that everything is working. As you saw in mine, like it had that like display error that just need to like tweak something. And yeah, just make sure that that runs. If that runs, and if you have no issue, that's great. If you're not able to resolve any issues that may come up, email me with the issue and I'll try and like help you solve that. And create your own case study with one scenario. So the specifics of this are defined in the next page here. So it's like create your own case study. First of all, start with a short amount of time steps so that you can get like a faster run and see that everything is connected well and you don't have any issues with that. And then increase the time steps to like go all the way to a full year. Try not to put like a very large list of assets. Keep it to like 10 or 15 assets tops in total, like into different locations should be good. And like still be able to run with this level in a reasonable amount of time. And the deliverable itself, you can send me screen captures of the terminal displaying those results. So this sort of like what this would look like. Add some saved images of the plots displayed when running the model. And a short paragraph describing what the difference of results could be when you run it with 192 and the 8760 in total. This is very reliant on obviously like you being able to set it up and like running through the workflow without any issues. And I know that like within the week we have like some time constraints. So if you can like definitely try it. If you run into many issues and it keeps being a problem, there's an alternative that we can do for the submission, which is if you send me CSV files that include like how you would have set up the case study. So you basically like set this up separately. You set the case study separately, that's at least one network structure and one scenario folder and where these technologies would be located. So it's like described here, the type of files that would be needed. A little paragraph to briefly describe like, okay, I chose these locations and these assets to choose it so that like I can sort of compare what is designed and what you have chosen. And writing a short analysis on what parameter you think could have changed in the plots presented on the next slide. So a quick explanation on what I mean by this. I have run the model. Let me put this bigger, sorry. I've run the model for 2 scenarios. So this is one single case study and 2 scenarios. All of the possibility of technologies installed are here. This is basically like the network structure that you'll have in the test collab case study. You have the size of assets in scenario 0 on this side and on a given scenario 1 that I'm not going to tell you how it was defined on this side. So based on these results, the sort of like that alternative assignment that we had here is a short analysis on what you think that parameter is. So the idea is that you analyze what it decided to install in this scenario versus this scenario and think like what could have changed. There can be different options, obviously, because I'm just giving you like this amount of information. But yeah, just think about what that could have been. I've labeled these for ease of sort of like analyzing this because it started looping through and repeating colors. So in this case, you'll see that this is electricity demand and this will be open field PV because it's not before. I need to label this just so that it's clear. But in this case, in this location, you have batteries and you have onshore wind, which are these 2. When I run this scenario, the colors are not repeated, so things are not labeled and everything should correspond. You'll note that there is no demand on location 2 because it was only wind. So just like watch out for those colors and figure out what the differences are. And the final little note is just to see that this goes up to 35 gigawatt, whereas this goes up to 140. The the label for gigawatt hour here, ignore that for now because different technologies have different like size units, but each one will have like their type. So for battery, this will be like the gigawatt, like the total size of the storage. Okay, so that's like the idea. Is this clear, or are there any questions on what the two possible like assignments that you can do are? Okay. Not seeing any question. Oh, something here. Oh, the due date of this. So, Indira, please let me know if there are issues with this for admin. So I will still be receiving assignments until like the Sunday 19th, until like midnight, so like 11:59. So that you don't like have to finish them by tomorrow, because tomorrow the assignment will help if you are able to set it up and have it sort of ready to help you throughout like Friday and Saturday and Sunday. Because the assignment tomorrow will involve some like data collection so that you can like continue testing and building and playing around with it. And the deliverable will be slightly different, but you will not need to have this fully completed by tomorrow. So yeah, I know that a lot of you have already sent me assignments from yesterday, which is great. And I've looked at some like really interesting stuff from there. But yeah, like just keep in mind, like you can submit it until Sunday midnight, so that we just can like take account of it for next week, to notify you of like participation and everything. But yeah, I know this might take some time and that people have other commitments, so don't worry too much. Awesome. And if for yesterday's assignment, if there are like any questions as well, like this would be yeah, a good moment. If anyone wants to like comment anything, please feel free. Hey, great. That's really, really good to read. I still have to go through a lot of them. I started with a few that I was able to see today. But yeah, so some like really interesting analyses and choices of systems. That was really, really cool and really nice. Thank you. Okay, great. Give like a minute or two if in case anyone else wants to like still type something or say something. But yeah, that should be the main things for today.
So sorry, so maybe just a reminder for everyone that I have sent you the link for the folder about the material, and then please let me know if you can't access it, and I will also upload the recording from day one until tomorrow. But I think it took time because the file is quite large, so maybe I expect it to be completed by tomorrow morning or in the afternoon. And Monica, please let me know if you have like any additional material or any revision that you did in the folder so that I could revise the material to become the updated one. Thank you, everyone.
Okay, perfect. Yeah, I'll let you know for that, and then maybe we can upload to that those resources into that folder. So like what I mentioned for the assignment for today. So then like people can directly go there and download it. Great. Perfect. Then yeah, if there's nothing else that comes up now, as always, if you think of anything and you want to like ask something or reach out, please feel free. That's what we're here for. And yeah, we can see you tomorrow. If that's it.
Thank
Perfect. Thank you, everyone. Have a good evening.
Bye.